Okay, this is the third part of the biochemical sequence here, and it's calcium. I've entitled it Calcium The Glutton. I kind of compare calcium to Henry VIII, whereas magnesium, which is also part of the lime complex, I would compare to Ebenezer Scrooge. Yeah, so magnesium is the miser, whereas calcium is the glutton. But both of these elements have that very grasping nature. And that's what I think of when I think of lime. And as I've said earlier, I consider lime to be more than just calcium. It's a complex. And calcium may be the most important member of that complex, but it also includes magnesium and even potassium and sodium. And for that matter, even your other cations, which might include iron, manganese, copper, or zinc, and even other trace elements. Now, if we are looking at calcium, this is a limestone formation in Turkey, and I thought it was just kind of picturesque. I've enjoyed Turkish figs a lot of my life. We had them when I was growing up, and they really love lime, and they can eat concrete, as they have eaten the concrete slabs of houses in Louisiana and Florida and whatnot, because once they started building houses on concrete slabs, nobody knew that fig trees did this. They planted them up against their houses like they used to when they built the houses like Queenslanders up off the ground. And so here you got a big Turkish fig tree, gets its roots underneath the slab, and 60 years down the track, the slab is crumbling in places. And come to find out that fig trees can eat limestone. So I thought it was kind of an interesting association to have limestone in Turkey. It's a hungry element because it's actually trying to give off 2 electrons and go back to the electron configuration of argon as an inert gas. But having said that, it's the basis of calcium oxide, calcium hydroxide, calcium carbonate, calcium sulfate, and all the rest of that. It wants to combine with things. And it's the basis of cement, of concrete, of plaster, and a variety of other such things that we use as glue to hold stones together in buildings or to make artificial stone. This is limestone quarry, and you can see here how calcium works on the horizontal. It was a sedimentary deposit from an earlier age of the earth, and it would have accumulated in a sedimentary basin of some sort, and what happens in these sedimentary basins, it's happening today in the oceans at a greater rate than we have historically experienced before. NASA sent up a satellite in 2003. They calculated the emissions of carbon dioxide into the atmosphere since the beginning of the industrial age, and that also was the industrial age of agriculture. We have given off easily as much, if not more, carbon dioxide off of our soil by burning up our soil organic matter than what we've done by burning coal and petroleum. But they couldn't find it in the atmosphere. Fully half of the carbon dioxide emissions that have been poured into the atmosphere since the beginning of the industrial age are not there. And so they thought, well, where are they? And some people said, oh, well, the carbon dioxide dissolves in the ocean. And then it reacts with calcium in the ocean waters, and magnesium for that matter, and it precipitates. And so this is what forms limestone. And we've got plenty of evidence that there's been a great deal of limestone sedimentary activity in the earth. And when we lime our fields, guess what happens? The acidity of the soil releases the carbon dioxide, and it gives off a lot of carbon dioxide just to lime our fields. And of course, as soon as plants are growing on it, then they're taking that carbon dioxide back in and turning it into carbohydrates. But in the meantime, the carbon dioxide emissions were fully like twice what, half what they would have been. They should have been twice what they are. And so they proved that the carbon dioxide actually is being turned into limestone and deposited in the depths of the ocean. So we're in an age of limestone formation. That's what happens to carbon dioxide. Huh?
So we might be able to become fossils and get in the calcium.
We could if we don't maybe do some things that are more proactive about this. Calcium is what fattens things, and calcium is capable even of dragging nitrogen out of the atmosphere. Now, it's not just calcium, it's calcium and magnesium, and of course, if it weren't for the activity of magnesium, that it's catching light and storing that as energy, then nitrogen fixation wouldn't work, because it takes 10 units of carbohydrates to manufacture one amino acid out of atmospheric nitrogen. And that relationship of 10 to 1 carbon to nitrogen carries over into a lot of things. Calcium holds things together, and I like that analogy when I think of this plant here. This is kudzu, of which I suggest that people might get a hold of Dan and listen to some of the things that he has to say about this, because being able to grow this plant is probably something that we farmers and grazers would very much like to do. If I was raising thoroughbred racehorses, then I would plant this in my paddocks, surrounded by bamboo, so that they couldn't eat it to death, and let the horses graze it off of the trailers that come over the bamboo. But horses also are a very highly demanding animal for silica, and if you wanted to have race horses with a lot of bottom that had strong bones and strong tendons and muscles and everything, and strong wills, then you'd have bamboo as a source of silicon and kudzu as a source of calcium. But those vines are terrific strength vines. It's a very vigorous binding plant that can, if it covered your house, it would lower the temperature inside in the summer by at least 5 or 6 degrees. A good way to insulate your house against the sunlight. If I was out at Alice Springs, I'd really consider it. Of course, it would be growing in the windows all around. If we think about this, calcium is on the male side of nature. We see this in a bull, for instance. He's got a lot more muscle and bone than a cow. The cow is actually giving off a lot of her calcium in milk, but the bull is accumulating it. And cows, as I might have mentioned earlier, the cow's horn is actually solid horn about the last third, and the bony structure inside is nowhere near as full as it is in a bull's horn. The bull's horn might be bigger in diameter, but it's hollow all the way to the tip. And it's got a bony structure inside that is a much more significant proportion of the calcium nature of the male side of bovine. We see this in flowers, that the pollen is where the protein and the calcium is, the nectar is where the silicon and sugar is. So we're looking at the opposite polarity to silicon in calcium, and it's the male side, whereas the female side, the silica side, is the opposite. Now in mineral formations, this is mineral formation, it's artificial, but you take limestone and grind it up, and you cook it off with coke, actually, to drive off the carbon dioxide and the moisture, and you may use some fly ash in that to make the concrete. And if you let it sit around and it can absorb moisture, it's a big worry if you're a shipper and you've got a shipload of freshly made cement powder. Then if you have a docking strike and you can't unload your cargo, then you're screwed, because it'll set up in your hole. It'll just draw the moisture out of the atmosphere. That's how strong and attractive force that calcium has. And that's what I am thinking of when I'm talking about its grasping, greedy nature. It's actually able to draw the moisture out of the atmosphere and lock itself up as stone. Without the silica in the concrete, it wouldn't be as hard as stone, but nonetheless it would be turned into stone. If you have a sack of this around the shed that you use part of it and then wrap the rest of it up, you come back and it's set up like a rock. Well, take yourself a good hammer or something and smash it up and feed it to your pig trees. They will love it. In terms of its biological processes, it lies at the center of things like our skeletons. So here we've got the cell nucleus of a cell is where the calcium ends up. The silica ends up in the cell wall. So the calcium is related to the protein, the DNA, in the nucleus of the cell, and the silica is related to most cells form in their cell walls, they form polysaccharides. These are complex sugars. They're not like sucrose or fructose or that sort of thing. They're really, really complex sugars, and they'll feel rubbery or gelatinous or so on and so forth, and they form that capsule around the cells. This is a plant, an herb, that's famous for its calcium activity, and it's got a very finely divided leaf, so it has a very good sulfur activity associated with it. But it's something that is sometimes used well, it's definitely used in biodynamic agriculture, and it's used to stimulate the calcium activity in the soil. Just one plant here or there is enough to stimulate the activity in a pasture or in a grain field.
What was the plant?
Chamomile. Matricaria chamomile. At the broadest level, calcium is working from the center of things. You heard in the Dennis Kochek lecture that he was talking about how things actually don't grow as an explosion that's coming from the center, the forces coming from the center. What causes things to grow are those forces that are coming from the cosmos. But interestingly enough, we're getting the materials that we build into bones and muscles, we're actually getting them from our senses. We're getting them from our surroundings. So the calcium that we eat, that we're eating as a mineral, doesn't deposit itself in our bones without those forces from the periphery putting it there. In other words, what builds it into our muscles and bones is actually the energy of our surroundings. And think about this. if you were an athlete or a bodybuilder, and like you wanted to be a footy player, think how much breathing you would have to do to build that muscular skeletal structure that it takes to be such a sports activist. If you were a weightlifter or something, you're not going to do this by eating, you're going to do this by exercise. The eating is just supplementary to the exercise. Without the exercise, you would never build the bone and muscle that it takes to do this. It's actually, if you're going to be a bodybuilder, you're going to get a lot of breathing. Now these are plants here. This one here I think is a soybean, very rich in calcium. This is another interesting one. Shabry's got this down there in their kimchi, and but you can see how this structure here, a big, broad, flattish leaf that sort of envelops things. So we're looking at calcium working from the earthly polarity, and it's sort of heavy and stays in place, and the activity is actually coming from the silica side of the matrix. In testing, standard test here for calcium in the CEC is an ammonium acetate extraction, and this is how we ordinarily measure the TEC and the CEC. It's the ratio that we use of calcium in the soil is not based on the needs of the plant. It's the needs of the soil. When we're looking for a certain calcium-magnesium ratio, let's say we have a soil that has a TEC of 16, or maybe even 20. We're looking for a calcium to magnesium ratio that's somewhere around 5 or 6 parts calcium to 1 part magnesium. The reason we're looking for that ratio is so that the soil will actually crumble and expose its surfaces. It's not because the plant needs that much calcium. It's because the plant needs to have the surfaces of the particles in the soil exposed to it. If you have a soil that has a TEC or CEC of 5 or 6, then you're looking for a ratio of calcium to magnesium that's more like 2 or 3 to 1. Because sandy soil doesn't have enough glue, so it needs to have a little more cohesion. It needs to be able to form soil aggregates so that you get these crumbs in the soil. And without a higher proportion of magnesium, it's a mechanical thing. The soil doesn't hang together well. So it's in calculating what the proper ratio is, it's a mechanical thing of whether the soil will hold together enough, but not too strong. If you had a soil with TEC of 70 or 80, then you're looking for a calcium to magnesium ratio of about 7 to 1, maybe even a little higher. And many of those soils are so full of magnesium in their total exchange capacity that they stick together like mad, and if you wanted to shift that ratio, you would find that maybe the magnesium is 40% of the CEC, and the calcium was only 38% or 36%. And you could put in so much calcium into that soil to shift that ratio where it was 6 or 7 to 1 that you couldn't possibly afford it in your lifetime. That's pretty daunting. So what I look at actually here is the total testing of the soil. And you would find that though the soluble testing gives you your TEC-CEC ratios, that the total testing may tell you that you have 10 times as much magnesium as showed up in the soluble test. And you might have 5 times as much calcium as showed up in the soluble test. You might have 40 times as much potassium as showed up in the soluble test. Now why is that? If you look at the mass of what's going on in the particles in the soil, an Avogadro's number is a gram atomic weight, and it's 6.02 times 10 to the 23rd power. Now, the significance of this is that even a speck big enough to see, like a clay colloidal particle, but you really would have to get a little magnifier to see it isolated. It's got so many atoms in it that it still has trillions of atoms in that particle, and only the ones on the surface are exposed. So it's an aluminium silicate. Clay is aluminium silicate by definition. So it's an aluminium silicate particle, and it's so fine that you couldn't see it in isolation all by itself. You'd have to have magnification. And yet, it still has trillions of atoms in that particle. Those trillions of atoms all have a slight charge. And it's a negative, it's an anionic charge, so it's attracting cations such as calcium and magnesium. But on your soluble tests, you will find that the cation that's most strongly attracted to that clay particle, the one that forms the innermost layers, because it'll form layers of atoms around it. Because it's got so many atoms inside the particle, to balance that charge takes layers and layers. It's encapsulated in layers and layers of atoms that balances charge. And the innermost ones will be iron. Iron has the ability to bind in the innermost layers of your clay particle, your clay colloids, more strongly than anything else. And magnesium is close behind it, not too close actually. Most of that iron that's in the innermost layers is so well enveloped by the layers around it that it isn't soluble at all. But these layers can exchange atoms, they can switch, and these atoms can migrate between layers. And it's very unlikely that you'd ever have a soil that had to have iron supplemented. It does happen, but it's unlikely. It's not very common. So if you do a total test, you'll see these huge, you've got 58,634 parts per million iron in that soil. You might have in the total test for magnesium, you might have 4,000 or 5,000 parts per million magnesium. There's that much difference. There'd be a 10 or 20-fold more iron content than magnesium. But the magnesium might have 10 times as much locked up in the soil as is on the surfaces, the outermost surfaces of those colloidal particles. And it doesn't take so much calcium as the sulfate to exchange in the outermost layer of those soil particles. So if you put your calcium right on the outermost layers, and your biology is using those outermost layers first, then you can shift the magnesium into the inner portion and lock it up. You conceivably can get the balance of those that are in the cation exchange, the readily accessible atoms. You can shift that balance. Anytime you see in your total test, you see calcium that is greater than what shows up in the CEC test, the ammonium acetate test, then you have the opportunity to draw calcium out of the soil's reserve and exchange it with magnesium. And soil biology will do those things where you physically couldn't get into the soil that time and get it accomplished. So it's something to think about. And what will happen in those clay particles is they will themselves, they also attract water in layers, and they also attract humic acids. And you get clay humus complexes in the soil, and that vastly improves your chances of unlocking those clay particles. And instead of them sticking to each other, like the clay in terracotta tile, then it'll open up and it'll expose its surfaces. So it really helps enormously to build humic acids into those soils. So you couldn't afford to get that ideal ratio in the cation exchange capacity of the soil by trucking in truckloads of lime. You'd be talking about putting 40 tons of limestone on per hectare. I don't know what your price of limestone would be, but if it was $30 a ton and you had to put 40 tons on, then could you afford it? I've seen heavy soils like that you calculate out how much it would take to put the calcium and magnesium in this ideal ratio, and you just can't afford it. So you do a little bit. I'll put a little bit of calcium sulfate out there, and it's based on what the ideal level of sulfate will be, not the ideal level of calcium. But if you can get just sort of like it's chipping away at that ratio, you really want the ratio, not because the ratio is something, something magical in itself, but because it opens up the soil. It's a mechanical thing. And if you can accomplish that mechanical process without adding all that lime, then it's much cheaper. And it's much more effective in the real. So, this is another picture. This is Calcium The Glutton, just incidentally. This is a type of perennial peanut. It's called perennial peanut in the States. It grows on real sandy soils. This is Arachis pintoi. It's called pinto peanut, and it's a similar deep-rooted legume. It makes a forage legume, and it makes a really good ground cover in orchards and trees. This one here will like clays a lot better. This one here has got a much narrower leaf, and it likes sandy soils. I've seen it in Florida, and sent its roots down through the sand all the way to the limestone, 60 to 80 feet below the surface of the soil. But it has to go a long ways. It may take it 3 years, but you'll know when it hits the limestone because it will take off. And it's a terrific pasture plant. It does not grow in the winter. None of these particular ones grow in the winter. If you undersow these with something like oats for the winter, they'll take over. This will go to sleep above ground, and it will grow roots. This one grows roots all winter. And then in the spring, when it comes back again, it's raring to go. So this is the kind of thing I like to see. These plants and the biology around their roots will release the calcium and allow the magnesium then to shift on the colon. So this is a very important part of remediating those soils, because the leguminous plants have that kind of activity that they can really shift the cation on the ground. In plant testing, tissue testing in plants, very similar to total acid digesting soils. And so what you see, because calcium is is so abundant in the cell structure of leaves that it's reported in percents. Anytime you're taking the percent, then it's if it's 1%, then that's 10,000 parts per million. If it's 1/10%, then it's 1,000 parts per million. So if you happen to be converting percents into parts per million, just multiply it by 10,000. When we see low calcium percents in leaf tests and high nitrogen tests, it's almost a sure sign of nitrates in the leaf. It's always a suspicious thing. And my experience is that the people who set the targets for these leaf tests for a variety of different crops, variety of different plants, that they were involved in the use of nitrogen fertilizers when they set those targets. And if I was giving advice to somebody and I want to protect myself from a lawsuit in case they used my advice and did something stupid and they blamed it on me and they're going to take me to court. And here I am, I get to court, and I start to explain why I suggested a certain recipe to the farmer. And I'm cross-examined. Well, where did you arrive at these targets? And I said, I set them myself. And so the cross-examination would make me look pretty arrogant as well as stupid if I didn't look to some peak scientific body, some university research where they set those target levels. If I just said, oh, I pulled it out of the hat, or I found it out by dowsing, or I thought it should be that. Well then, I need to back this up and say where I got those parameters. Where did this come from? I need to say, oh, well, Queensland DPI or Queensland University or something else like that, that's the target levels they set. Now I've seen the target levels set by the University of Hawaii on a number of crops, ginger, taro, etc., would be 1.5 times greater, maybe even greater than that what was set by the Queensland DPI. They've got something going on in Hawaii where they go mad with nitrogen fertilizer. And they set these extremely high targets to grow the worst quality ginger, the worst quality taro you can possibly grow. And so I can pick and choose, to some extent, which set of parameters I use as my targets. But I have to be a little bit circumspect in setting targets that there's some other authoritative source for the targets that I set. So I may suggest that nitrogen target there is, if it was amino acid nitrogen, well then it would be lower. It wouldn't be up there in the middle of that range that was set by some university or CSIRO or whatever. But if it was amino acid nitrogen, there'd actually be less. Ammonium is the percent of nitrogen in ammonium is something like 70% or something. Whereas we're looking at protein, true protein, would be a measure of nitrogen multiplied by 6.25 to give us the protein content. So if I was going backwards on that and figuring the nitrogen content, then I'd have a lower, if it was true protein, I'd have a lower amount of nitrogen than if it was ammonium. So what I find in plant testing is I have to test for nitrate ammonium in order to know whether this actually, the nitrogen is true protein or whether it's some poison salt, really. I mean, it's not too toxic, but it is somewhat toxic. when I was a kid, I sang in the choir, and we had the choir stall was full of these little vials of ammonium acetate, and it's called smelling salts. And if the sermon was too boring and you're ready to pass out, then you take the lid off of that, and you get a little hit, and boy, it wakes you up. Then you'd be ready to sing when the time came. It's called smelling salt. I don't recommend that you do that with anhydrous ammonia coming out of you. Now the story with that stuff, it's a gas, and it's like pure anhydrous ammonia, and it's being injected into the soil, and you've got a tank that you're dragging behind you. You've got a sort of a ripper blade that is shooting gas into the soil. You're injecting gas into the soil. And if you were working on this thing and the hose blew off and it sprayed it, then you would be, forever after, you would be blinded. The eyes would just be white.
It's really good stuff for you boil it.
Huh?
It's really good stuff for you boil it.
Oh man, it does that to your biology in the soil too. Man, is it reactive stuff. Yeah, somebody like that, where I lived in Georgia, we'd say, you know, he's cotton-eyed, because his eyes would be completely white. Wouldn't be able to see out of them, of course, but that's one of the dangers of using anhydrous ammonia. Just incidentally, this here is a 4-leaf clover, and this is a 5-leaf clover. This is a 5-leaf clover. If you have got the calcium amino acid form of lime in your soil, then in the embryonic cell division of the leaf, where the leaf is first being formed in the plant, if you really have a fertile activity in the soil, then you will get twinning of clover leaves. And in this case here, it would have been the middle leaf that twinned. See? And so you end up with a 4-leaf clover. In this case here, it would have been not only the middle leaf that twinned, but another leaf that twinned. And it's not so uncommon then to have 6-leaf clovers too. And those are always a sign of really good calcium metabolism in the soil. You've got such good reproductive, and the reproduction of the DNA in the cells is a calcium process. And you've got such a good reproductive process that the embryonic leaf twins. Someone, maybe it was Jason, was telling me how many twins he got in his cabin this year, and that's a sign of fertility. In the dairy business, however, if you get twins, and one of them is male, the other one is female, then the female of the twins will be a free market. She won't be fertile, she won't ever conceive.
Why not in the dairy industry?
Well, you don't care that much in the beef industry. You know, it'll be true in the beef industry too. But if you're in the beef industry, well, it doesn't matter so much. You just put them in with the yearlings that you're raising and whatnot. But in the dairy industry, it's very important to have heifers to replace your dairy cows. And if they won't conceive, then they won't milk either.
So is the male fertile as well?
Yeah, I don't know how fertile the male is either. It wouldn't be my pick for my bloodline.
What about the sheep?
Huh?
Wouldn't be the same as sheep.
It could be. I don't know. I don't have enough experience with sheep to know, but I sure have the experience with dairy and all that.
You can genetically breed for twins with sheep.
Huh?
You can genetically spec for twinning.
Yeah, well, I've seen, in fact, the fellow who was showing me this was a sheep breeder, and he was getting not only twins, but triplets in his, with his ewes, in his lamb. So he was he was frequently getting triplets.
Mick
And it's the
wasn't
same
overly happy.
phenomenon. If he's getting this, then he's probably getting triplets.
Hugh,
Yeah.
what about the 15th set of twins last year? Mick Windsor wasn't very happy.
Yeah, but Mick Windsor is a dairy farmer who every one of his paddocks is loaded with 4, 5, 6, and what did we find? We found 7-leaf clovers.
1-7.
1-7.
Yeah, but lots and lots of 5s.
Yeah, I never have seen an 8. I have seen 9-leaf clovers. Twice in my life I've seen 9-leaf clovers, but I have never found an 8-leaf clover. There's something going on there. It's just, but it is a calcium thing that happens. This again is that soil that we were looking at. Let's look at the calcium this time. Now, what we actually had in this soil was we had 2016 parts per million. Our target, based on an ideal CEC, would have been 1937. So we're topped up on calcium in the cation exchange capacity. Actually, you'll notice up here in the cation exchange capacity, at a pH of 7, then the cation exchange capacity and the total exchange capacity are the same. Now, even above 7, that would be true. Okay, the total exchange capacity is full at a pH of 7, and that means that the cation exchange capacity doesn't have any hydrogen in it. It's full of other cations. So, looking at that, I'm topped up on calcium. If I look over here, I've got even more calcium, and I have another almost 700 parts per million calcium. I've got more than 700 parts per million, 750 as it happens, above the requirement for having an ideal level of calcium. However, my magnesium component here, I'm 107 parts per million above the target. In other words, the magnesium part of the CEC it's over the top. What I would be looking for would be 205 parts per million. In my total test, I have 1199. So the amount of extra magnesium in my total test is like just about 1900 parts per million. I only have an extra 750 of calcium, and I have 1900 parts per million extra of magnesium. So that explains there what I was saying about the magnesium being more tightly bound in the inner layers of the colloid. With potassium here, I've also got an excess of potassium in this soil. My range of potassium, ideal range in the CEC, is much lower, but look at how much potassium is in the total. There's enough potassium in this soil that the grandchildren of this dairy farmer would never have to add. What happens though in many cases is potassium levels fall below, say, this bottom target range, and if that's all you're looking at, then it's a good chance to sell potassium in NPK fertilizer. If you put the potassium in there, however, it's not really a benefit because it tends to get in the way of the uptake of magnesium. And it's very common on the plant tissue test, and we'll look at that in just a minute. It's very common to have high magnesium soil and low magnesium in the leaf. And it's not so uncommon to have the potassium show up high in the leaf, and it is getting in the way of the uptake of magnesium. So really what we have to do to chase potassium availability in soils is we need to get phosphorus working because it allows the soil's microbes to get the energy out of the root exudates, the sugary root exudates. If the phosphorus provides the means for unlocking the energy in the sugars, the microbes will keep feeding the potassium from the soil's less available reserves. So let's look at this in the plant. You can see already here both calcium and magnesium are deficient in the leaf. And it's just what I said in that regard. But actually in this case, the potassium is also deficient in the leaf. So what you look for to see, well, wait a minute, what's going on, then you look for other factors. If the boron is low, then you can't get any of this stuff up in the leaf. You see that? Here we've got low boron in the leaf, and it's the basis of sap pressure. You look at silicon, and silicon is low. Well, the transport system isn't able to carry enough of any of those other things. You have them in the soil, but you can't get them in the leaf because, first of all, boron and silicon aren't working. And then the rest of the stuff, it's chasing your tail to put NPK fertilizer on you. It would be like taking a bucket of money and going into your compost operation and pouring it out and running your compost turner through it.
So how much is the phosphorus sort of taking the place of the silica and suppressing the potassium and so on?
Okay, I wouldn't say the phosphorus is doing much of any of that, but the phosphorus does get carried up and deposited. This wouldn't be growing worth a hoot. And the phosphorus would build up because there's not enough calcium for cell division. There's, the other stuff isn't happening. There is phosphorus gets up there because the phosphorus has the uptake. It has that little bit of cationic activity. It's working between calcium and silica. See, neither calcium nor silica is getting up there well enough, but the phosphorus working between it does. And it only does that because the plant isn't using it once it takes it up.
I mean, you see the ammonium on the nitrate is very high, but at the top it says nitrate N is in target or almost a little bit low. Why is the nitrate ammonium high and the nitrate is low?
Well, high pH is going to push nitrogen towards the ammonia side rather than the nitrate side. If the pH was below 7 in this soil, I think you'd see a different ratio between nitrate and ammonia.
But on the top, the first line says nitrogen?
Yeah, the nitrogen there is, the nitrogen, see in this test, the nitrogen figure is arrived at by combustion and spectrographic analysis. So this is how much nitrogen's in there. But there's a huge amount of that nitrogen that is ammonia rather than protein. See, crude protein says it's 20.5%. But actually, the true protein is a lot less than that, might be 15 or 16%, because a lot of that nitrogen is actually in the form of ammonium, and a fair little bit is in the form of nitrate. But I've seen these things. I can remember one in bananas where nitrate was like 15 or 1800 parts per million, and ammonium was 6 or 700.
So these two tests have nothing to do with the nitrogen at all?
Oh yes, they do. These two tests have a lot to do with the nitrogen up here. The nitrogen looks like it's okay, but it's not amino acid nitrogen. It's pumped up artificially with nitrate and ammonium salts, and that's using up the plant's energies in the leaf, trying to convert these things into amino acid, so the plant isn't going to have any leftover sugar for root exudation to feed the soil biology. And then the whole thing ends up in a heap.
So if nitrate and ammonia are low, you assume you've got more true protein, even though we haven't got a test that says true protein equals this.
That's exactly right. If the nitrate and ammonium are low here, we can be, I'd say, certain that this is true protein rather than artificial, figure for protein. This 3.3% nitrogen up here is actually, it would be more like 2.5% if it was actual amino acid nitrogen. We just about have to look at these bars down here. And if we don't test for nitrate and ammonium, and it's a separate test, the lab doesn't run these at the same time and doesn't run them the same way. And so, if we don't ask for these figures from the lab, and we don't get them, we would think maybe that the nitrogen was fine. And that the problem is silicon and boron, and to some extent then we'd be able to get the calcium into the plant. But, hey, in the leaf, one of the problems here is there's not enough molybdenum in the leaf, and the molybdenum is the basis for converting these things into amino acids. If you don't have enough molybdenum in the leaf, then you won't be able to convert these properly, and probably one of the best things we could do in this case is to give it a little foliar molybdenum so that it would be able to convert these, and then it would have energy left over for root exudation, and then you would have these other things would have a much better chance of getting into the plant.
So, back to our previous session, wouldn't you be saying that the high nitrates and ammonia is actually tying up the boron? That it is the high nitrates that are causing the trouble, to the boron?
Well, yes, I would say the high nitrates are causing a heap of trouble here. And that really flushes the boron out of the leaf. It flushes it through the system, and if there's any root exudation, then it goes back down.
Yeah, if that's inverted, you've got a higher nitrate than ammonium. Is that any indication of just what you put on, or is there a function that's happening?
I'd certainly look at what I put on, but this can happen also if we have a period of dry weather and then we suddenly get it wet.
Right.
So then what happens when you suddenly get wet is the protoplasm in the microorganisms in the soil is released, it oxidizes or it ammonifies, in this case ammonification because of the high pH, and then you get these situations and you didn't put it on, it just was the way that it occurred because of the weather. But to move along here, there we see this is oftentimes, and it is a calcium shortage in the tomato, but it's not caused by the calcium shortage, it's caused by the boron shortage, and so is this. This is a shortage of boron because it couldn't, this is the stem end, the blossom end, it never got the nutrients out towards the end of the zucchini. And here we see what's happened with nitrification in the central rib of these lemons. And that nitrate uptake there, it buggered the calcium uptake in the plant. How could you get calcium or any other nutrients through that? And the stem end of the lemon requires that all the nutrients go down that central pithy rib and then get distributed back into the juice of the lemon from the blossom end. And when that's messed up in the middle, well then that won't happen. And we can put on limestone for calcium, because that isn't going to cure the blossom end rot, it isn't going to cure the styler end rot, because it's identified as calcium deficiency, and it is a calcium deficiency, but it's not caused by a lack of calcium. So these mineral remedies really need to be put on along with a food that feeds them into the humic acid structures, the actinomycetes, and mycorrhizal fungi. So I would suggest using humic acids for that. You could use these plants either to draw up calcium or to be recycled for building calcium in the soil. And I like the plant remedies because it's building biological calcium. It's not the same as putting on limestone. I particularly like kudzu, as I've said before. This is kudzu, this is kudzu, this is kudzu. It's terrific. Boy, is it a plant that knows how to grow, which makes it an object of fear by a lot of people. But if you were to put animals, livestock grazing this, they would completely kill it if you didn't get them back off of it again.
Well, I seem much the same as kudzu in the way it works.
Yeah, it's just nowhere near as robust a plant. Glycine is a vine like that, but it would never cover tall skyscrapers or cross long bridges. Yeah, it grew halfway across the Mississippi River Bridge at Natchez before they killed it. That's a 2-mile long bridge. Yeah, this is in that rosette stage. This plant is a calcium plant, but it's so much of a silica and sulfur and boron plant that if it gets enough of those things, it'll do its job and it'll die, of course, after it makes seed. It's good to let it make seed so that it'll be there in case you ever need it again, but it won't come back in a case like that, chances are. And animal sources of calcium, again, your effluent water, your compost, and even feather meal. Those are good sources. And you're also looking at things like dung beetles recycling it, earthworms recycling it, and interestingly enough, fungi hold on to it. They don't let it leach. So what I would suggest always in these remedies, both plant and animal based, is to make sure that you pattern them. And we're looking at these processes, these patterns. This is making cow pat pit. This was in India. This this was horn clay actually on my farm. This was horn manure on my farm. Biodynamic remedies. There's also these remedies in the biodynamic realm of the so-called compost or herbal remedies. This one here is the chamomile remedy. You pack the chamomile flowers in these small intestines from a cow, and you make them up like sausages. And you have to protect them. This was hanging them in the summer. I experimented with that because Steiner suggested you could do that in his agriculture course. And I hung them up in the sun for the summer and then buried them over the winter. But animals will go after them because they perceive that energy that they accumulate. This one here in the middle, stinging nettle, is probably my all-time favorite remedy for the whole range of nutrients. It's a cure for anemia, and it has to protect itself, I guess. This is a very awareness-provoking plant, and